Alright, so number 5 is a work problem. It says suppose 5 joules of work are needed to stretch a spring. So as soon as I see the word spring, I know it's going to be one of these spring problems. We know the force of a spring is equal to kx, where k is the spring constant for that specific spring, and x is the distance the string is stretched from its natural position, natural length. And then work is going to be the integral from a to b of kx, or the force of kx dx. So basically we figure out what k equals, it goes there, and then we're ready to go. And there's two ways they can go about doing this. They can either tell me what the force is and allow me to know the distance that it's been stretched from its natural position in order to find k, or they can tell me how much work has already been done for some stretch. So depending on what they do for this, that's how we're going to go about doing this. So this one says 5 joules of work are needed, so we're going to be using this formula here in order to find k. And it says the natural length is 10 centimeters. It's important that we know what the natural length is. And it's being stretched to 18 centimeters, which is an 8 centimeter stretch. So we know x is equal to 8 centimeters. But it's very, very important that we're going to, oh, and you know what, I'm not going to go with x equals 8 centimeters. Let's go with a and b here. So a is equal to something, b is equal to something, and a and b represent how far away we are from the natural length. So the natural length of 10 centimeters is the starting point, so we're going 0 centimeters away from the natural position, and we're stretching it to 18, which is 8 centimeters away from natural position. But hopefully you guys remember that when we're dealing with work and the unit is joules, we want newtons and meters as our units, and so we don't want centimeters. So 0 centimeters is the same as 0 meters, 8 centimeters is 0.08 meters. To go from centimeters to meters, we simply divide by 100. So looking at this picture here, I know A, I know B, I know W, I do not know K, and X is going to be the variable that we're going to be working with. So if I fill in everything I know, 5 equals integral from 0 to 0.08 of kx dx. So if I evaluate this integral, it's going to be kx squared over 2 from 0 to 0.08. That's supposed to equal 5. If I put 0.08 in, square it and divide by 2, so 0.08 squared divided by 2 is 0.0032. So 5 equals 0.0032k. If I put 0 in, I get 0, so subtract 0. So 5 equals that. To find k, I just have to do 5 divided by 0.0032, which comes out to 1562.5. Once I know what k equals, now it says, the next statement here says, how much work is needed to stretch the spring from 15 to 20 centimeters. So this spring constant of 1562.5 is the spring constant. So what I know is that the work accomplished that I'm looking for is going to be the integral of kx, which is 1562.5x dx. And we're going to go from the start to the finish. We're stretching it from 15 centimeters to 20 centimeters. And again, I have to compare that to the natural length of 10 centimeters. So 15 centimeters is 5 centimeters beyond natural position, and 20 is 10 centimeters beyond natural position. 5 centimeters equals 0.05 meters, that's what goes down here. 10 centimeters is 0.1 meter, that goes up here. And then it's just another integral to evaluate. This time I know everything over here, so I'm trying to find W. So W is going to equal 1562.5 x squared over 2 from 0.05 up to 0.1. If I evaluate with 0.1 first and subtract when I evaluate with 0.05, so 1562.5 times 0.1 squared divided by 2. So putting in 0.1 gets me 7.8125. And if I put 0.05 in, 1562.5 times 0.05 squared divided by 2, that comes out to 1.953125. So to find the overall work, I just subtract those. So 7.1825 minus 1.953125 3125 comes out to 5.23, basically 5.23 joules. So expect a problem of that general nature there. I will give you the work and how, I'll tell you what the natural length is, how far it's been stretched, and you'll use that to find K, and then once you know what K equals, you need to find the work for a different stretch. And again, always compare it to the original natural length, and also again make sure all the units are in meters when we're dealing with newtons, meters, joules. Number 6, a force of 50 newtons is required to maintain a spring stretched from its natural length of 20 centimeters to a length of 22 centimeters. So, force of 50 newtons, this time they're not giving us work, they're giving us force. And again, our force equation is Kx. My job is to figure out what K equals. So if I use the information they give me, 50 newtons is the amount of force. And the spring has been stretched from natural length of 20 to 22 centimeters. That's a 2 centimeter stretch. So I know x equals 2 centimeters, but again I know x needs to be in meters. So 0.02 meters. So K times 0.02 equals 50. If I just do 50 divided by 0.02, we get a K value of 2,500 on this one. Once I know what K equals, again that's my force function. Force is 2,500x. And to find work, I need to integrate the force function. And I need to go from the beginning to the end of the stretch. So we're stretching it from 20 centimeters, which is the natural length, so that's 0, up to 30 centimeters, that's 10 centimeters, which is equal to 0.1 meters. So again, meters, meters, make sure those are in meters. As far as evaluating the integral is concerned, we take 2,500 x squared divided by 2, going from 0 up to 0.1, that's just 1,250 x squared. And then again, just substitute 0.1 in first, so 1,250 times 0.1 squared comes out to 12.5. If I put 0 in, I'm going to get 0. So the answer is 12.5 joules. So 2 different ways to do a spring problem there. One where they give you work, one where they give you force. Make sure you're comfortable with both techniques. Both techniques require us to find K. And once we find K, this product is pretty much the same on both. The difference is how you find K. Number 7, also we're looking for how much work. And when we're dealing with units of feet and pounds, we're going to look for a unit of foot-pounds. So we want all of our units of length and feet, all of our units of force in pounds. And what we have here is a 4,000 pound car that's suspended by an 80-foot cable that weighs 20 pounds per foot. Alright, so it's important that we have the correct force function here, which is basically the weight of everything that's being lifted. So if you just imagine what's going on here, here's this pulley of some sort, or winch maybe, that's got a cable attached to it with a car at the end of it. And the length of the cable is 80 feet. So the initial position of the cable is 80 feet long. And if it gets all the way up here, it'll be 0 feet long. So just imagine the length of the cable being the x variable that we're dealing with here. We're trying to raise the car 40 feet. So from the ground, 40 feet high. So that's the beginning position of 80. Their ending position is going to be 40. Alright, and as this cable gets pulled in, the weight of the cable is going to get less and less and less. So right now, initially, 80 feet long, 20 pounds per foot, that's 1,600 pounds of cable. But as it gets pulled in, we're getting less and less cable, so the weight of the cable is getting less. The car stays 4,000 pounds. It's going to stay the same weight all the way through. So if we look at a force function for this, the weight of the car is constant. So 4,000 pounds is just the weight of the car, not going to change. The weight of the cable is 20 pounds per foot, so 20 pounds per foot times the number of feet there are, which is going to be x in the problem here. And that's it. That's everything that's going into the weight of the car. So we have constant, we have a variable weight. This is changing as x gets smaller, this gets smaller. So we started at 80, we're at 1,600, we end at 40, that'd be 800. If we ended at 0, it'd be 0. So the weight of the cable wouldn't weigh anything at that point. But again, we're stopping at 40. So once you've got your force function established there, we're going to integrate to find the work. and we integrate the force function, which is 4,000 plus 20x dx. Now, it's very important that we get the interval correct here. So when we're dealing with this, again, let 0 be the top of the cable. So 0 is no cable, 40 feet of cable, 80 feet of cable. When you're dealing with one of these cable problems. Our ending point is the bottom number, and our starting point is the top number. So we're going from 40 to 80. All right. And again, if you just imagine x represents how long the cable is, we want to get involved the two numbers that represent the weight of the cable at each position on this problem. So that's kind of a way of thinking about that. You always go small to big, and again, 0's at the top, 80's here, 40's there. So the length of the cable is the bottom. How far we're trying to get up to is the top. And then once we get that all figured out, we simply have to integrate 4,000x plus 20x squared over 2, better known as 10x squared, going from 40 up to 80. We substitute 80 first. 4,000 times 80 plus 10 times 80 squared comes out to 384,000. Again, that's just substituting 80 in. I want to substitute in 40 also, so I don't want to subtract that. So I do 4,000 times 40 minus 10 times 40 squared. And that comes out to 144,000. So 384,000 minus 144,000 comes out to 240,000 foot-pounds. All right, so 3 work problems. Again, expect similar structures to the problems, similar types of techniques to be used on the actual test. Numbers 8, 9, and 10 all deal with average value of function. Number 8 is just a kind of warm-up average value function. We want to find the average value of g on the interval from 0 to 2. And our average value formula tells us to take 1 over the interval length. So from 0 to 2 is 2 spaces. We're going to integrate that from the beginning to the end of the interval of the function x squared minus 2x plus 4 dx. Just a simple polynomial integral. We're going to evaluate the integral, put the 2 and the 0 in, and multiply the answer times a half. So 1/2 kind of just sticks around. Antiderivative of x squared is x cubed over 3. The antiderivative of negative 2x is negative x squared. The antiderivative of 4 is positive 4x, going from 0 up to 2. If I put 2 in first, I get 8/3 minus 4 plus 8. Subtract 0, I'm going to get 0 minus 0 plus 0, so I just get a bunch of zeros. Inside the brackets, common denominator is 3, so I'm going to get 8 minus 12 plus 24/3. That's just going to be 1/2 of 20/3, which equals 10/3. 9. The temperature of a metal rod 10 meters long is 10x in degrees Celsius, the distance x meters from one end of the rod. So if the rod is here, and the length of the rod is 10 meters, and we got position 0, position 10, the temperature is 10x. So over here it's 0 degrees Celsius, over here it's 100 degrees Celsius. Our job is to find the average temperature of this rod. And I will say on the test, I'm not going to stick to a linear function necessarily. It might be a different power, but it'll be some sort of polynomial structure. Then with the average temperature of the rod. So what I do is to find the average temperature, I simply integrate the temperature function, 10x in this case, from the beginning to the end of the rod. And I got to multiply that times 1 over the length of the rod. So be careful that 1/10 gets in there. And the antiderivative of 10x, of course, is 5x squared. We're multiplying that times 1/10. We substitute 10. 10 squared is 100 times 5 is 500. Minus 5 times 0 squared is 0. 1/10 of 500 is 50 degrees Celsius. So I expect it to be a metal rod. It will be some length. And again, 1 over the interval length. We're starting at 0 going to 10. And and then of course we're going from 0 to 10 there too, so whatever this is, subtract those to get that number. And finally, number 10, find the average value of the function. This one's a little bit more challenging because the integral is a little bit more difficult. It's the same technique basically as number 8, where you're going to integrate this function over this interval and 1 over the interval length involved too. So the average value of f is going to equal 1/2 integral from 0 to 2 of x cubed times the 4th root of 16 plus x to the 4th dx. So the first thing I notice is I have a radical structure here. I'd rather have a fractional power structure, so I'm going to actually change that to parentheses 16 plus x to the 4th power. Now, this is a power structure, so it's a power type function. I want this piece of it to be u. And then I have to establish du for that u, so du is going to equal 4x cubed dx. And I'm hoping that du is within the problem. If it is, I'm good to go. If not, I have to fix it. So I've got a dx, I've got an x cubed, but I'm missing the 4. A constant problem is fixable, so if I put a 4 inside, I've got to put a 1/4 outside. That just multiplies by the bottom. So this is u to the 4th power, 4x cubed dx is du. So the problem switches from its current structure into, this is u to the 4th, and this is du. This is 1/8 out here. And then finally, I need this interval here to be a u interval, because right now, this is dx, so that's x equals 2, and that's x equals 0. U equals 16 plus x to the 4th, so 16 plus 0 to the 4th is 16, so 0 becomes 16, going from x to u. And 2 to the 4th is 16 plus 16 is 32, so 2 becomes 32. 2 is x, 32 is u. And now I've got this integral to do, which is pretty basic. It's going to be u to the 5/4 over 5/4. Be evaluated from 16 up to 32. And I can't get an exact value for 32 to the 5/4 power, so at this point I'd probably just approximate. So if I type in my calculator 4 times 32 to the 5/4, and when you type in 5/4 caret, make sure you put parentheses 5 divided by 4 in parentheses, so that whole fraction power gets there, divided by 5. And that gives me 60.8874. And if I put 16 in, I'm going to get 4 times 16 to the 5/4 power, again parentheses 5 divided by 4 in parentheses, divided by 5. And that comes out to 25.6. So if I take this minus this divided by 8, we're going to get the answer. So 60.8874 minus 25.6 equals, divided by 8 equals. And we get 4.4109. So we'll go 4.41 a couple dozen places. The average value of f is 4.41.